In this session we will give you the details, the actual math of the variational model method, and you may wonder where the name itself comes from. Well, you remember what it actually does. It's a method, fairly simple method. You'll see the math this session and the next. The math is quite simple, and there's no ICBST. It can be shown that, which is nice for a change. It's all there, and fairly simple. And what it's about is it's a fairly simple method that allows you to estimate the ground state energy by you just guess what you think is a reasonable ground state wave function, and you plug it into you use that estimated or guessed, or the German word is Ansatz, like a trial function, something you think might be correct, and you test it. It's a trial as in trial and error, and you calculate the Hamiltonian, you calculate the expectation value of the Hamiltonian, so angular brackets h hat, using that Ansatz, using that trial function, which we will call T for trial. I could have called it A for Ansatz. I know the textbook uses T. They don't talk at all about Ansatz. That's more a math term. But the higher level math physics guys are using it now because they're so exposed to the math. Like I say, I've been saying several times, at the highest ends, pure math and math physics have merged. Those two sets of guys are effectively one set. So why variational? Well, you can put parameters, is the critical idea. You can put parameters into that trial solution, and then you'll then get the expectation value of the Hamiltonian here. You will then get that expression as a function of your parameters. And you can then minimize this expectation value for the Hamiltonian by just doing high school calculus to minimize this value, which is a function of the parameters. Now, in this session and the next, we'll keep things fairly simple. We'll just use one parameter, which we'll call alpha, again. Lots of alphas in different contexts, and different meanings. This time it's just a parameter that we can vary, and hence the label of the technique, the variational model or variational method. Okay, so that's sort of the essence of the idea. And so, well, and there's a little bit of math. There's one theorem, but it's pretty easy. Okay, so you guess. So the essence of the technique is that you're guessing a possible ground state wave function. So let's just call it here ut. Right? And then we compute the expectation value of the Hamiltonian. Now, why do that? Well, because we're trying to find the eigenenergy, the lowest energy, the ground state energy, which by definition is the lowest energy. Right? So E0, in other words. So with this Ansatz, this trial solution, we hope is as close as possible to the ground state wave function. In other words, the wave function whose eigenvalue is E0 gives you the lowest eigenenergy, E0. Okay. So now, if this were U0, the lowest eigenstate, for giving whose eigenvalue is the lowest energy, E0, then H U naught would be E naught. Sorry, yeah, E naught U naught. Okay, so the E naught would be a constant that would come out here, and then you got U naught U naught. Well, that's just one because these are the eigen functions of the Hamiltonian are an orthonormal set, right? So bra ket will give you just one, and you're just left with E naught outside. Okay, so effectively what you're trying to do is to guess a trial function, an ansatz, that's as close as possible to U naught, that gives you this expectation value of the Hamiltonian to approximate as closely as possible your E naught, your ground state energy. Okay? So this whole approach is basically trying to find a trial, an ansatz, call it here UT, such that the expectation value of the Hamiltonian is minimum. In other words, as close as possible to E naught, the ground state energy. Okay, that's the motivation. That's what you're trying to do. Now, why does it work? Okay, so it boils down to minimizing this, having plugged in a trial function, an ansatz, UT. Okay. Well, this is this, right? 3 bars by definition. It's just the overlap integral from many lectures back. Okay. Now the proof. There's a little theorem here. This here is greater or equal to the true ground state energy. In other words, E naught. Okay. That's the theorem statement. Now I'll try to prove it, and I'm using now the pure math notation. So theorem statement. That this is greater or equal to E naught, the true ground state energy, and followed by the proof of that statement. So proof statement, proof, and at the end of the proof, an end of proof marker, indicator, signal saying, hey guys, this is the end of the proof. And it's useful because if you're learning something for the first time and you're not familiar with it, it's often the case. It's not, you're not certain where the proof finishes. So it's very helpful to have an end of proof marker or sign. And there are various signs used. The old one was QED, Latin. I've done this before, a bit of revision again. Quod is in Latin. Quod erat demonstratum, which means as was to be proved, which effectively says, that's the end of the proof. Okay, but nowadays, more modern texts, and I do note, like I have many GTMs, as I call them, the graduate level mathematics textbooks, famous, published by Springer, German multinational academic publishers, Springer Verlag, publishing company, and I'm noticing, the last 5-10 years or so, there's now pretty well a convention established amongst the mathematicians that the end of proof marker is this vertical hollow rectangle, right? Like this. So this is supposed to be a rectangle. A bit older, sometimes people fill this in, so it'd be like a black vertical rectangle. Some people used to say, as was to be proved, or thus completing the proof, stuff like that. So, but nowadays it's this. All right. Okay. Back to the actual proof. Now, what are we trying to show? We're trying to show that this expectation value has to be greater or equal to the real ground state energy. In other words, E naught. Okay. All right. Well, so we have to calculate this and show that it is greater than the ground state energy. So that's the strategy of the proof. Choosing a method, an approach said this before, but a lot of truth to it. Choosing an approach to proving something is like half the battle, because the rest of the work depends on your strategy. So that's where the creative genius comes in many cases, of creative mathematicians who prove things. They often have a hunch